Welcome to Global Information Security Society for Professional of Pakistan.
So my name is Syed Hasan. I've been working as a DFIR consultant in Pakistan for the last 2 years. Now, we know memory forensics is one of the most important processes in a forensics investigation. Although we'll uncover that later on, for this particular video, I want to focus my attention on memory acquisition on Linux systems. And we're going to see techniques as to how we can acquire memory while ensuring that our forensic footprint on the target system is minimal. So we ensure that the evidence is not destroyed by our own activity. Let's take a look. Memory forensics is one of the most vital parts of a forensic investigation. Since the memory is extremely volatile, that is, it has the capability to overwrite evidence extremely fast, we prioritize acquisition of memory much earlier. So if you had plans on maybe acquiring the disk of the target system, you have to prioritize it after acquiring the memory of the system, right? Because in this way, you're going to acquire the memory first. That is, you have a snapshot of the volatile data, and then you're going to try and focus on the non-volatile data that is your disk. Now, why do we actually perform memory forensics? Again, it is extremely easy to perform. You can actually easily acquire it, although we'll see a few problems that we can face during memory acquisition on Unix. But again, it is much easier to acquire in contrast to maybe terabytes worth of disks. So our servers, servers run primarily run Unix systems these days, although that is not a necessity, but I'm generalizing things here. So if these servers do in fact run a Unix system, you're going to see large disks attached to them. So if you're going to perform disk forensics, you're going to have to set aside some time, for example, maybe a day, for it to acquire, verify the image, and then you can maybe begin your analysis on top of it. But for memory, let's say it has maybe 32 gigs of memory, right? And that is only going to take you maybe an hour at max. Going to take you an hour to collect it from the target system. So again, it is quite easier to collect from the system. The issues it has, we'll discuss those later on, but the issues are again extremely overweight by the fact that memory is a stronghold for tons of artifacts. You're going to have processes, you're going to have network connections, you're going to see what loadable kernel modules are in there, you're going to see what the user attempted to do in a particular timeline. You can run Yara on top of it, and there are endless possibilities to what you can do on a memory image of a Unix system. Now, one of the problems that we do face is that it is a tad bit difficult to acquire it on a Unix system without leaving some form of footprint on the system. What sort of footprint is there? We'll see that in the later section. But maybe you'd be wondering, what if I use a commercial tool, right? And if I do use a commercial tool, right, maybe fresponse, it can help me collect memory from a system without leaving some form of footprint. And that is not exactly true. You are paying a huge amount of money for that, first of all, for the license. And then these tools typically bring their own LKMs, which are loadable kernel modules. So these modules themselves, they pose a risk, because when you are going to load a module into the system, you have some form of risk. That is, you're going to modify the memory or the target system. So whenever maybe you do copy that particular agent of that tool on that system, you're going to modify the file system of that system. If you are going to maybe execute that binary, you're going to overwrite some form of evidence in the memory for process executions, and so on and so forth. So this, you have to understand the risk of it. And if you do accept the risk, that is, you do know what you're doing, and that it is not going to mess around with your investigation, then for sure you can invest in such tools, and that'd be great. But if you're hoping to see a few open source projects, or maybe open source alternatives to commercial tooling for memory acquisition on Unix systems, let's see a few options in the next section. Acquiring memory on a Unix system can be a bit difficult, but we do have several techniques thanks to these open source tools using which we can acquire memory rather quickly. Now, before I get started with my list, you can see I have mentioned a few interfaces here. For example, proc-k-co, devmem, and devcrash. So these interfaces, or otherwise, some of these are actually character devices. Now, these character devices are basic interfaces such that the kernel allows indirect access to the hardware device. So using the interface, for example, devmem, I can simply access the actual physical memory of the system. Now, unfortunately, after Linux kernel versions 2.6.x, we do not have direct access to these interfaces. So we have to either load a kernel module such that the module is going to access the interface or the character device for us, or we have to find some other technique. And luckily, there are solutions which do not require LKMs as well. For example, here's the first one. AVML, Acquire Volatile Memory for Linux. It was an open source tool released by Microsoft, and it does a tremendous job of acquiring memory from a target system. It can acquire the memory from three main interfaces, the ones I've mentioned before as well: proc-k-co, devmem, and devcrash. Now, you do have the ability to select the interface yourself as well. So you can specify the source of the memory, and if that source is available, the memory will be collected from that particular source. Now, on Ubuntu systems, proc-k-co is generally available to us as an interface, and it is quite easier to access it using AVML, but devmem is not. Now, there are also options in AVML to such that you can ship this compressed or decompressed memory snapshot to a different system, or maybe to the cloud. This is excellent because in cases you do not actually want to modify the local file system, you do have the option to ship it somewhere else. Secondly, we have LIME. Now, LIME stands for Linux Memory Extractor. LIME is simply a loadable kernel module. Now, this LKM is going to be built on the same system, and when I say the same system, I mean that the kernel versions of the target system must match the system at which LIME was built. If the kernel versions match, then the loadable kernel module is actually going to be executed just fine. Now, you can use the command insmod, which we're going to see later as well, and using that command we can simply execute the module. Thirdly, we have LinPMem. LinPMem uses the proc-k-co interface, and finally we have FMEM, which uses the devmem virtual device. Now, usually these utilities, you can say, are actually available on GitHub on their respective websites, and we can download them from their release pages. If you're not happy with the build version, you can compile them yourselves. Now, there are several issues which you might face. For example, when you are trying to build a LinPMem, you might see that it has several dependencies. Now, if you are completely fine and you do have experience with building binaries yourselves or compiling them, you can do that. But for this educational video, you could say, I'm simply going to use the versions which are actually in the actual releases of the GitHub repositories. Now, let's move on to the demonstration. And if there are so many tools to acquire memory from a Unix system, what is actually the difficulty faced by investigators in acquiring memory? It's actually the kernel. You see, if you are going to use a tool which has loadable kernel modules, that is drivers, you cannot actually use that without making sure that the LKM and the target system both have the same kernel version. That is, the module itself, that is the kernel module itself, should be built on the same system as the one where you're going to run it. So that actually means that you're going to compile the driver on the same system as your target machine. And we cannot actually do that in a forensic investigation, because we are going to override evidence on the file system or disk while we are compiling the LKM. So what are the solutions to this problem? You can either completely avoid loadable kernel modules. Perhaps you can use AVML to acquire memory from the Linux system. Or for the second approach, this is going to be a bit extensive, but what you can do is you can create a machine in your environment which has the same kernel version as the target machine. So in your environment, you can compile or build the loadable kernel module, and then you can transfer it over to the target system, and then you can execute your memory acquisition script or binary or whatever you want. So this way, you're going to have at least some footprint, but it's not going to be as massive as it would be if you were to build or compile the LKM on the same system as the one where you are going to investigate something. Now, before we continue with the demonstration, let's focus on memory analysis. Now, we can use a tool like Volatility to analyze the memory snapshot that we've acquired, and we can then continue with the analysis. It has the ability to parse data structures and run scripts on top of it, that is plugins on top of it, and acquire artifacts from the memory snapshot. However, parsing memory using Volatility also requires a kernel specific profile. So basically you have to build Volatility as well on the same system as the one on which you are going to execute Volatility. Or actually, let's rephrase that. You're going to have to build Volatility such that it has a profile with the kernel version which is the same as the kernel version of the memory snapshot that you took. So basically, the kernel versions of the Volatility profile and the memory snapshot should be compatible, because Volatility basically uses these kernel specific profiles to parse your memory dumps, because every kernel is going to have some form of data structure which are different from the one before it. So if you use incorrect kernel versions to parse your memory snapshots, you're going to have some form of difficulty making sure that they are both in sync. And the output is basically going to be garbage. So again, a solution for this is the same as the one for using memory acquisition scripts. That is, you can build Volatility on a machine with the same kernel version as the one from which you're going to acquire the memory. I do not recommend executing scripts on a target system on which you are going to basically perform your digital forensics. So that is not a recommended approach. So you're going to have to build a system with the same kernel version as the target machine, because that is likely the only recommended approach. If you do know a different approach and you feel that it is much better, maybe you can share it in the comments below. Now, finally, let's head into the demonstration. We are going to acquire memory from a Unix system that I've created in my environment, and we are going to generate the Volatility profiles for it and see how we can dump artifacts from a memory snapshot. Now that we're in the demonstration, let's check out AVML and other tools in our list. Now, I've basically pulled out every tool that I've mentioned in the listing before, and now we're simply going to test out how we can use them and acquire memory on a Unix system. Now, for the first one, we have AVML. Now, for AVML, you can simply go into the releases section of the GitHub repository, and you can pull AVML and other utilities such as AVML convert and AVML minimal if you want, using this release tag. Now, I've simply pulled them out. Now, by the way, if you want the links to these websites or perhaps commands which I'm going to execute, I'm going to put up a link in the description of this video where you can use my gist that I have kept on GitHub, and you can use all the links and commands from there to perhaps acquire memory on your own Unix system. All right. So we can see that AVML has several features. That is, it can save recorded images to external locations. It can retry execution. It even has page level compression, and it can use the LIME format, which is easily readable and parsable by Volatility. Now, it can acquire from three memory sources, which we've discussed before: devcrash, proc-core, and devmem. If the memory source, basically, if you're not going to provide the memory source to AVML, it is going to select whichever one is available on the current system. Now, let's take a look at a few commands. All right, so I've basically pulled out AVML here. Let's simply move into the directory, and I'm going to list it out here. So, for example, we have the AVML binary over here, right? I'm simply going to run file on it, and we can see that it's an ELF binary. Now, if we try and run AVML here, if I can show you the help, we can see that it is a portable volatile memory acquisition tool, and we can simply provide the flags to it. Maybe I should extend it a bit so we can see it over here, right? And I can compress it, maybe delete the file upon successful upload, and otherwise. Now, using the source, parameters, we can see over here, we can also specify the input source. The possible values are proc core, devmem, and devcrash. So simply, I'm simply going to use AVML over here, just like that, this binary, and I'm going to select perhaps compression because I want to compress the file, and then I'm going to select the source and see. Let's see if my system has the devmem interface or not, right? And then I'm going to pass the file name to it, and let's say that is compressed mem.lime.compressed. All right, and let's pass that out. Now I'm simply going to pass my password, but it cannot do that. Now the reason for that is that it was unable to. Okay, maybe we are unable to access this particular interface, right? What if we try and capture the memory from the proc core interface? All right, so it's doing it. Now it is actually acquiring the memory live as we are. I do not wish to skip my commands. Now if you can simply run ls, and I can show you. So this output at lime is an uncompressed memory sample which I acquired earlier, and the compressed lime compressed, you can see that I acquired right in front of us. That is just of 620 megabytes. Now it's quite compressed. You can actually use AVML converter to decompress this and perhaps use it in your memory investigations. But you can see that it did not take that long. It took a few minutes perhaps, and without loading any form of kernel module, it has provided the system memory to us, and that is excellent. Now, although I'm using the local file system for it to actually write the file name over here, you can perhaps pass it to the memory to a different file system. Perhaps you do have USB mounted on your Linux system, or maybe you do have some cloud storage perhaps. Let's see if AVML can show us support for that, right? And we can see that it has support for SAS via Azure Blob storage, or if we have perhaps a different server, we can also upload the memory via HTTP port upon acquisition. And further, if you wish to delete it without actually writing to the file system, you can use the -- delete parameter with AVML. So that should be it for AVML. We're going to later see if we can actually use these with volatility, and what information can we pass with this acquired memory. All right, next we have LinPMem. Now LinPMem also has other alternatives such as WinPMem and OS PMem, which are used for Windows and the Mac OS operating system respectively. But for this particular example, we have LinPMem acquired, and this is the GitHub repo for it, which is CAFF4, which is actually the advanced forensics file format. And this LinPMem can basically be used to acquire the disk of a particular system and the memory as well. Now we can see over here that this project implements a C++ library for creating, reading, and manipulating AFF4 images. It also includes AFF4 imager binary, which provides a general purpose standalone imaging tool. Now we can also use LinPMem, which is again shipped with this particular project, which is right over here, to simply acquire memory from a Unix system. I've simply acquired this over here, and we can see that the binary is available. Now let's run it with sudo, and maybe I can show you the help command of it. All right, so it has several parameters. By the way, if you have seen that this is actually released by Google and incorporation, right? So this was later incorporated into the recall memory forensics project, which was again run by Google, but later discontinued because Google shifted its attention towards GRR, which is the Google Rapid Response project. Now let me basically shift to the top over here, so we can use the binary over here. We can pass the format of the file that we want to acquire the memory in. I'm simply going to use raw for it because it is actually easier for me to convert later. I'm not going to use the volume format. I do want to acquire the memory, so I'm going to use -m with it. And finally, so we don't actually need the page files or etc. We want everything in the memory. So we're not going to specify something specific over here. Right, I believe I'll be needing the output as well, right? So I'm simply going to pass the output file as well. And I guess that should be it, right? So let's start executing it. So sudo, and I believe that's LinPMem, and I'm going to pass the format to raw, and I'm going to pass -m and perhaps -o for my memory dot raw. Let's see if it works, right? So all right, so it's going to acquire the memory for me, and let's see if it is the same as the one acquired by AVML right before. So my system, by the way, does have 2 gigabytes worth of RAM, and that is exactly why we are seeing 2 GBs worth of RAM. All right, so we're going to see. All right, so it's 2.3 gigabytes worth of raw memory, and we can later use that in Volatility. Next up, we have Lime. Now, Lime is a loadable kernel module which allows for volatile memory acquisition from Linux and Linux-based devices such as Android. Now, we have simply pulled the repository right here. I'm going to move into the folder, and I'm going to go into src, and we can see that there's a make file right here. Now, to execute the instructions in the make file, I'm going to run the make command. Now, since I've already run it, the kernel module has actually been compiled together and moved into this my current directory. So I do have it, and I can now execute it using I believe, let's actually try and insert the module using nsmod. I'm not sure if I've already done that, but we can see what happens, right? All right, so we pass 5, and then we're going to pass the path to it, which is going to be, let's say, my memory.raw, or actually line. I'm going to pass the format, which is equals to line, right? I'm going to execute it, and you can see that it is going to execute and dump out the memory of this particular system in the line format. Now, again, the only flaw over here is that you are actually meddling with the system, such that you're inserting a module, you're actually compiling it on the system, if you are, and then you're going to execute and see if the memory is actually available or not, right? So if I can check out my memory, we can see that it's actually a 2 gigabytes worth of file, and it is available in the Lime format. So you've simply acquired memory from the system using Lime, which is the loadable, which is the Lime memory extractor, which is a loadable kernel module. Now, next up we have FMEM. Now, FMEM is again another tool which can help us acquire memory from a system. It creates the dev FMEM device. This virtual device is going to be created, which is directly mapped to the dev mem virtual device, I believe. Now, and it can be used to dump out the physical memory. Now, I've simply pulled out the repository here again. Now, if we can go to FMEM, and we can see that it has several files, and it does have another fmake file. So again, using the usage, we can see that we have to first run a make, which I've done already. Then we're going to run the run script, which is right here. I've converted it into an executable, and we can simply going to run it, and then, which is basically going to produce our let's say the dev fmem virtual device. You can see over here that since I've already run.sh, it has created the virtual device for me. Now, when I'm going to run dd from it, now if you remember, I mentioned that earlier investigators were able to simply use a command such that, for example, this, right, dd if, which is the input, and I'm going to pass devmem to it, and I'm going to pass the output to, let's say, my memory, if I can type correctly, my memory.raw, and I'm going to pass the block size to be 1 MB, and I'm going to count. So I'm going to have 2000 blocks, right? Because it's a 1 MB block size. Now we cannot actually access the devmem character device yourselves. The Linux kernel does not allow you to do that, but we can actually access dev fmem, which is created by this fmem tool. And simply, if I can pass dd, right, just let me verify the command dd. I've passed the input to be dev fmem. I've passed the output to be my memory.raw, I've passed the block size to be 1 MB, and I want 2000 blocks to be captured. Now, if I actually do not pass the count to this particular command, it's not going to be executed, or actually it is going to execute and keep collecting memory until your system actually crashes, right? Because here's why. So if you do something like DD, IF, and OF, that is, you do not pass the block size or the count to it, the DD will never stop, even if there's no more physical RAM on the system. This is a feature because the Linux kernel version does not have a stable API, and detection of mapped areas can be tricky. So we're simply going to pass the count to 2000 because we know that our memory is 2 gigabytes. I'm simply going to collect it, and we can see if my memory is going to be available or not. Let's give it a few minutes. And all right, so you can see that it has copied out 2 gigabytes worth of files, and if I can run my memory, it's actually my memory, and you can see that the memory has been acquired using FMEM. Now for the next part of the video, what we're going to do is we're going to focus on creating a profile for Volatility 2, so you can analyze the memory sample which we have previously acquired. So you see, just as you were able to create a loadable kernel module by targeting the specific kernel version of your Ubuntu system, in my case an Ubuntu system, similarly Volatility also requires a profile which matches or is actually compatible with the kernel version from which the memory snapshot was acquired. So why does it actually need it? It's because each kernel version, I mean, it might have different data structures or debug symbols which are necessary for Volatility to parse those data structures and acquire the data from the memory sample. So for this particular example, what I'm going to do is I'm simply going to acquire the repository of Volatility. I've simply pulled that repository in my local folder, as you can see over here. And for output.lime is basically the memory image which we acquired from AVML, right? So I'm simply going to head into the Volatility folder. Now Volatility does actually provide you support so that you can easily create profiles for your specific kernel versions, right? So I'm going to go into the tools and Linux folder, and you can see there's a make file over here. So I'm simply going to run the make command, and it's going to execute and generate the module.dwarf file. Now, if you have some trouble in executing the command within the make file, you can either append a sudo with it. It's likely because it is trying to access files which are in folders which you cannot easily access from your non-privileged user. So you can simply try and run sudo make. If that does not work, and you might see a different error, for example, you might see an error like dwarf dump is not found. So dwarf dump is basically a utility which you require to build compile together this dwarf file. So if you don't have that, you can simply run sudo a command like apt-get install and maybe dwarf dump, right? So that is going to install it for you. Now, since I have that, it's not going to install it for me, but now you have the module.dwarf file. All right. Now that we have the dwarf file with us, now the dwarf file is actually what contains the data structures which Volatility needs to parse out the structures from the memory. Now one thing is left. We need the debug symbols. Now debug symbols are available to us in boot, and we can check them out with the all right, so I believe I have, let's try that. Right, so that is fine. So you can see it's ls and into the boot directory and the system files. So you can see the system.map files. I have 3 particular files which are mapped to different kernel versions, right? Actually, the kernel version is same. It's the release which is a bit different, right? So we can check it out over here, and we can see that the current version is 5.8.055. So I'm simply going to acquire this one, and I'm going to zip both of these together. That is my module.dwarf file and the system.map file which contains the debug symbols. So let's run the zip command. Maybe I can do something like linux.zip, and I'm going to move the module.dwarf file in it and the boot system 55, right? And I'm going to run sudo with it because I'm accessing a file which I probably do not have access to. So now that we have linux.zip, I'm simply going to move the linux.zip into, all right, actually let's go back in. I'm going to move linux to dot. All right, so here I am. Let's clear this out. So you can see it's in my root volatility folder. I'm going to clear it. Ls again. Now let's go into volatility, and then into plugins, then into overlays, and finally into Linux. This is the folder you want to actually keep your profiles, right? So for this particular version, I actually created a profile right before starting this video. So you can see that my profile is already here. Now I've named it a bit nicely because if I want to recreate this analysis, or maybe I want to reuse these symbols and data structures in a different investigation, I can use them. And this name actually helps me memorize them, right? Because I have the distribution name and I have the kernel version name in the same file name, basically. So you can rename your linux.zip file in the same manner if you want. Now that we have this, then let's go back and try and execute our let's try and execute volatility on the output.line file, right? Now a thing with volatility 2 is that you need Python 2 to actually execute volatility 2, right? So I do have the 2.7.18 with me, and now what I'm going to do is I'm going to clear this again, ls, and I'm going to run vol.py, right? And I'm simply going to run info on it. It has a few issues with grep. If I can maybe grab Debian here, we should have an idea, right? All right, no. Let's look for Linux. Maybe that should help us an idea. All right, so you can see that this is the profile here for us. Now it has a profile for Linux. The distribution is Ubuntu, and the kernel version is this. And that is my architecture, which is x64. Now this is the profile name which I'm going to use to basically parse out information from my memory image. So let's try and do that, right? So I'm going to run vol.py again, and I'm going to pass the image to it using tick F. Let's go back to output.lime, and I'm going to give it the profile. Let's copy that. Actually, that does not work. I'm going to right click and paste it. And now we're going to run one of the plugins, right? So one from the top of my head is netstat. Let's try and execute netstat. So this is these errors are basically due to the Windows based plugins which are trying to execute, and obviously they cannot. Now right, so this error is because I do not have the required permissions on my output.line file. For this particular example, I'm simply going to give it privileges to try and parse it out, and it should give us some results really soon. All right, so you can see that here's an output of netstat on my memory image. All right, that's quite a lot of output, but that at least gives you an idea that you can generate a volatility profile for your particular system based on the kernel version, and you can get started with your analysis. Now it's time to conclude this video. Now in this particular video, what I've done is I've shown you how you can acquire memory from a Unix-based system while ensuring that your forensic footprint on that system is minimal, because you do not want to destroy evidence while you're trying to collect it. Next, we saw how we can compile together a profile for volatility which can be used to analyze memory images. Hopefully in a later video, we can also explore how we can use volatility to analyze these memory images and extract information out of them to help in our digital forensics investigations. Thank you so much for watching this video. If you have any comments, feedback, please leave them in the comments below. I'd love to hear your feedback and maybe answer your questions if you have any. Thank you. Goodbye.